Hi. So we are doing chapter number 16, counting and choosing. And up to now, we have covered binomial coefficients and binomial theorem. Now we will talk about binomial coefficients and multinomial coefficients and multinomial theorem. So let's try to do that. So let's say, suppose that 8 students, call them 1 to 8, are to be assigned 3 projects. Suppose 8 students, call them 1 to 8, are to be assigned to 3 projects. And let's call those projects ABC. Now, project A requires 4 students. Project B requires 2. And project C requires also 2. In how many ways can the students be assigned to the projects? Students be assigned to projects. Okay. To answer this, we could list all the possible assignments like this in a table. So let's say you have A, B, and C. And equation 1, project 1, A, we assign first 4, then 5, 6, and 7, 8. Then again, first 4, then 7, 8 to project B, and 5, 6 to project C. Then first 4, then say 5, 7, and 6, 8. Then again first 4 to project A, and we say that 6, 8, and 5, 7 to project C. And then let's change 1, 2, 3, and 5. And then 4, 6, and 7, 8. However, the deadline for the projects will probably have passed by the time we have finished writing down the complete list. Interesting. So the deadline for the projects probably have passed by the time we have finished writing down the complete list. In fact, there are 420 possible assignments. So in this table, there could be possibly 420 possibilities. So we need a nice way of counting such things. So each assignment is what is called an ordered partition of the set which has 8 elements and subsets A, B, C of sizes 4 to 2. So here is a general definition of such a thing. Definition. We say that let n be a positive integer and let S contains n elements a partition of the set S is a collection of subsets S1 to Sn or K such that each element of S lies in exactly one of these sets. The subsets the partition is ordered ordered if we take account of the order. Order in which the subsets are written. So we have n elements in the set. We have k subsets, which can be partitions of the set. And each element of the set S lies in exactly one of these subsets. Okay. The point about the order is that, for instance, in the above example, the ordered partition so in above example, the ordered partition is 1, 2, 3, 4 in the first set, 5, 6 in the second set, and 7, 8 in the third set is different from the ordered partition one, two, three, 4 in the first set, 7, 8 in the second set, and 5, 6 in the third set. Even though the subsets involve the same in both cases. So if, a point to note, if R1 to Rk are non-negative integers such that n is sum of these R1 to Rk, we denote the total number of ordered partitions of S the set which has n elements into subsets S1 to Sk of sizes R1 to Rk by the symbol that n choose R1 to Rk. Okay. So these are the total number of elements in the set S, and these are the sizes. These are the sizes of the partitions of the set S. Okay. So let's give an example. (16.4) 1. The number of possible project assignments in the example above is the number of possible project assignments in the example above is given by this n. Choose R1, R2, R3, where we have n is equals to 8, R1 is 4, R2 is 2, R3 is 2. Okay. Number 2, example number 2, if some Alfred Barney Kedrick and Duglade play bridge, the total number of different possible hands that can be dealt is is 52 from 13, 13, 13, 13. Number 3, it is rather clear that n choose r, comma r n minus r is nothing but n choose r, right? So let's define how we calculate this number. So by a proposition, (16.4). So we said we have n choose R1 to Rk is given by n factorial, R factorial, R1 factorial, R2 factorial, product to Rk factorial. And we can prove this proposition. We say that we count the n factorial arrangements of the set S, which contains n elements in stages as follows. So we say stage 0 is choose an ordered partition of set S into subsets. Sk of sizes R1 to Rk. The number of ways of doing this is this. Now, stage 1, choose an arrangement of S1. There are R1 factorial choices. Stage 2, choose an arrangement of the set S2, and there are two factorial choices, and so on until we have stage K, which has choose an arrangement of the set Sk, and there are K factorial choices. Then, by the multiplication principle, we conclude that n factorial is nothing but n into R1 or K choose multiply R1 factorial up to K factorial. And this follows the result. Okay. By doing this, we can trace this by finding an example. So, number 1. So for the project assignments, we had that 8 choose 4 to 2. And we can find it out by solving this expression. And if you solve it, we'll get 420. Number 2. So to solve 52 choose 13, 13, 13, 13 is approximately 5.365 multiply 10 power 28. It's a quite large number. So From there, we say that the numbers and choose R1 to Rk are called multinomial coefficients. And the reason is the following, and define as a theorem. Theorem 16.3 named multinomial theorem. Okay, so we say that let n be a positive integer and let x1 up to xk be real numbers. Then the expansion of x1 plus 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 up to xk power n is the sum of all terms of the form and choose R1 to Rk power x1 R1 dot dot xk power Rk, where these R1 Rk are non-negative integers such that their sum is n. Perfect. And let's prove this. So we consider the expansion of x1 up to xk power n as the product of these brackets n times. Okay. In expanding this, we get a term where we have x1 power r1 dot dot xk power rk by choosing x1 from r1 of the brackets similarly x2 from r2 brackets and so on, and the number of ways of doing this is nothing but and choose R1 RK. So this is the coefficient of x1 power R1, xk power RK in the expansion. And there, this is how we prove this theorem. Now let's use this and specify and solve some examples. Example 1, the expansion of x plus y plus z cube is x plus y plus z cube is nothing but x cube plus y cube plus z cube plus 3x square y plus 3x y square plus 3x square z plus 3x z square plus 3y square z plus 3yz square plus 6xyz. Okay, perfect. Number 2 is the coefficient of x square y cube z square in the expansion of x plus y plus z power 7 is nothing but 7, 2, 3, 2 choose, and that is 7 factorial, 2 factorial, 3 factorial, 2 factorial equals to 210. Okay, number 3. Find the coefficient of x cube in the expansion one minus 1 over x cube plus 2 x square whole power 5. Solution would be a typical term in this expression is is 5 choose a b c multiply 1 power a into minus 1 power x cube power b minus 1 over x cube power b into 2 x square power c. Now where a plus b plus c is 5 and a comma b comma c are greater than or equal to 0. To make this a term in x cube, x cube, we need that minus 3b plus 2c is 3 and a plus b plus c is 5. So from the first equation, three divides c, so c is 0 or 3. Now if c is 0, then b is minus 1, which is impossible. Because if c is 0 and b is minus 1, then a needs to be somehow 6, but that is more than 5. So another one is all of them should be greater than 0. So b can't be minus 1. Hence, c is 3 and it follows that a is 1, b is 1. Thus, there is just one term in x cube. X cube, namely, that is 5, 1, 1, 3 minus 1 over x cube 2x square cube, and that is minus 160x cube. In other words, the coefficient is of x cube is minus 160. Perfect. So that is how we can deal these propositions and define the multinomial theorem and coefficient. See you in the next lecture. Thank you. Bye. Please do subscribe the channel and like it.